Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 46 and in this lecture we will be looking into another readout circuitry which is basically multiplexers and circulators, widely used in the case of quantum computers in quantum computing region. So the outline will be, we will be studying into multiplexers, the role and need for cryo-multiplexers, their challenges, look into circulators, then look into the importance of cryo-circulators specific to our domain in the microwave domain, and then look into limitation, advances and challenges which we face in a circulator. Now, if you look at the superconducting qubit here, there are two types of qubits which are available commercially or otherwise. Superconducting qubit is one of them which is used. So, typically superconducting qubits are typically addressed by dispersion, right? They are addressed by dispersion, right? And these dispersions are coupled to a resonator. So, basically what we do is that we send a signal, a microwave signal that goes to the qubit, gets reflected back, and as it reflects back you measure the frequency of the signal which has been reflected back and then try to corroborate what is the state of the qubit by looking at the change in the frequency of the signal which is available to you. So, this is basically known as state dependent frequency shift, right. So, this is known as a state dependent frequency shift. So, depending on the state of the qubit, and this is basically qubit state dependency frequency shift is there. Now, there are typical when you do a readout circuitry, in a typical measured formulation, then you will have receivers, right, you will have wireless receivers will be there. There will be also large amount of low frequency, intermediate frequency amplifiers will be there, which we have already studied, which is an LNA at cryo temperature in our previous state. Now, these needs to be matched properly, right, and one of the important aspects therefore for readout circuitry which comes into picture is basically known as multiplexers, to keep into this digital idea here. So, let us look at the multiplexers. I hope all of you are aware of it. Just to refresh your memory, this is basically a combinational circuit which selects one output out of multiple inputs, right, and who does that? The select line. So, there are two inputs here, for example this, and there is a select line here. This is known as 2:1 multiplexer. 2:1 means 2 input and 1 output. So, 2:1 multiplexer. You can have 4:1, you can have 8:1, you can have 16:1 multiplexer, which means, for example, what is the meaning of 16:1? It means that there are 16 inputs which are coming simultaneously to this multiplexer. I can select any one of them by using the select line S, right. So, that is how you define a multiplexer, right. And so, for example, if there are 8 input lines, or there are 4 input lines, you require 2 select lines. If there are 8 input lines, you require 3 select lines. If there are 16 input lines, you require 4 select lines. So, basically 2 to the power S is the number of inputs. So, if there are 2 to the power 4, which means there are 16 inputs out of which you can select one of the inputs, right. And why is it? So, this works in the digital domain, not in the analog domain, right. Now, the selection is controlled by as I discussed with you, binary select lines, and what does it do is it tries to reduce the number of required data lines. So, basically the input is so Y is the shared bit line which is available to me, shared path. All the input will be shared on Y. So, you basically do what? You reduce the number of interconnects in the output side. That is the advantage of having a multiplexer. Now, let us look at the role and needs. So, as I discussed with you, so if you look at the dilution refrigerator, some of my initial lectures, they are quite complex and complicated, right, and you do not want that the wiring which is going from the qubits working at millikelvin temperature down and then to 4 Kelvin electronics and then to the external interconnects should not be too. So, you need to reduce that wiring bottleneck. You do not want the wiring to be so large in number. And the reason being very simple, you do not want the wiring to be large in number because you do not want large thermal noise or large thermal budget also to be inserted. and that's where multiplexer tries to reduce the number of wiring. It also it helps you to enable communication between classical control platforms and cryogenic quantum hardware. Let me show you, maybe I have a graph to show that. Yes. So this is my quantum state, and this is where my electronics are there. So multiplexer acts as an interface, right, between the quantum qubits and the readout electronics. So they act as an interface between the two, right. So let me come back here and show to you. So this we have done, then we come to this. So this is basically what we are trying to do, is that the multiplexers tend to enhance the throughput, right. Why? How does it enhance the throughput? Because if there are, say, n number of qubits available, right, and all are giving the output signal, you don't want, you say the nth qubit signal to be outputted, you can use a select line to get that nth signal to be outputted through the multiplexer. And that is the reason it acts as either as a parallel or a sequential access design for multiple quantum devices. So there are multiple quantum qubits available, say there is a 100 qubit quantum system available, and you want to access only the 5th qubit design, right. You want to get the signal out of the 5th qubit. Then by using an external select line, I can actually instruct the multiplexer to select that signal and throw it in the output side. So what you have done basically is that you have reduced the wiring. Otherwise you would be using 100 wires to route the signal to the output side. That adds to the thermal load, right. So that is the reason multiplexers are important, and especially in the cryogenic domain. It reduces the thermal load, right, and very understandably so, because your cabling cost reduces, your cabling complexity reduces, and you actually work at very, very low thermal budgets and thermal loads in case of cryo multiplexers. Multiplexers do support cryogenic electronics at 1 to 4 Kelvin, and we have very low noise, right. The multiplexers typically are combinational logical blocks, and they are digital in nature. So the noise is, even if it is crosses the threshold, it is below the threshold, that can be rejected very easily, and it has got a very low latency in terms of signal processing. In terms of signal processing, the latency is very low, which means that the amount of time taken to process any signal is relatively low in case of a cryo multiplexer, and the noise floor is also very, very low. Now we have also seen that the multiplexers and demultiplexers both are there. So if you come back to this slide once again, if you look at very carefully, you have a multiplexer which goes to the readout circuitry, but there is a demux also here which tries to control the qubit. So there are both multiplexers and demultiplexers are opposite of multiplexers. Multiplexers tend to have multiple input signal and one output signal, whereas demultiplexers try to send one control signal into multiple output signal. So it is something like this. I want to control, let us suppose, the 6th qubit, and there are 100 qubits available. By using an external source, I can instruct the demultiplexer to control only the 6th qubit and do not touch the other qubits, right. So it is something like that in a much more, in a sort of a layman language, I am using it at this stage, just to give you an idea what is a multiplexer and demultiplexer. They are scalable. First of all, the multiplexers and demultiplexers are scalable, which means that you can scale it down to, say, n number of inputs. What is the n number of inputs? You can have 2 inputs, you can have 4 inputs, you can have 8 inputs, you can have 16 inputs, and therefore their scalability is very easily maintained in a multiplexer. That is the added advantage of a multiplexer. Now let us look at the cryo multiplexer here. They are generally designed to operate from DC to about 10 gigahertz and a wide temperature range, right from millikelvin. So your mux should be very, very robust in the sense that it needs to operate over a wide frequency range from a DC bias, which is 0 frequency, to 10 gigahertz, and we need to be sure that while operating in such a large frequency range, your power budgets and noise floors do not get compromised, right. And the temperature range is typically from few millikelvins to few kelvins to about 300 Kelvin, which is the room temperature. Now let me rub this part and just show it to you. Let us look at this left side schematic here, and this is basically a schematic of a large scale characterization platform, right. for a quantum DUT, device under test, or multi-bit processing platform. So, I have multiple bits, qubits, and I want to process it. So, first of all, look at this structure here, which is kept at 0.01 Kelvin, which is somewhere around 10 millikelvin, right. So, at 10 millikelvin your qubits are being kept. Low temperature, you know why, because you do not want to lose the state of the qubit by increasing the temperature. So, they are kept that. The multiplexers are kept very close to the qubits, right, and the multiplexers tend to therefore give you an output depending upon the variety of inputs here. The readout electronics is kept at 1 to 4 Kelvin, right. All the readout electronics is kept at 1 to 4 Kelvin here, you see 1 to 4 Kelvin is there, and all your computer interface, user interface is kept at room temperature. So, you have wires which carry signal from multiplexers to readout electronics, and you have wires which carry from readout electronics down to the computer interface, user interface. This is where the user sits and tries to control it. Now, how does it control it? It uses what is known as a RF control electronics, right. So, this is an RF radio frequency control, it is typically high frequency control which you give, that controls the demultiplexer. Demultiplexer controls the qubit. Qubit output comes to the multiplexer sends it to the readout electronics, and so on and so forth. While doing all these things, please understand that the temperature which is mentioned here needs to be maintained for the full mode of operation. It cannot change beyond a particular point. It needs to maintain that same temperature across the cryo-multiplexer. Now, let us look at the cryo-multiplexer. Again, as I have already discussed with you, if you have serial interfacing, then if there are 4 qubits, then you require 4 digital lines. If it is basically parallel interfacing, you require log n to the base 2 plus 1 digital lines for n number of ports. So, if there are say 8 ports available, you require certain number of much lower number of lines, whereas if you require 8 ports available, then basically what you will get is, so let's take n equals to 8, right. So, we get log 8 log 2 and this is 2 to the power 3. So, 3 plus 1, you require 4 lines for parallel interface, right, whereas you require actually 8 lines for serial interface. So, you see, just by increasing the number of lines, a number of ports, serial interface gives you a much larger number of lines as compared to parallel interface. Similarly, the program, so if you have a serial interface, the time required to program the serial interface is much larger as compared to a parallel interface, right, and that is written in the third bullet which you see, that the programming time for serial interface scales linear with the number of ports. So, if you increase the number of ports to 2, 4, 6, 8, 10, so on and so forth, the time required to program it increases linearly. That is not the case when you do for parallel programming. And that is the reason you see the last fourth point, that the digital line count, which is the number of lines which carries the signal, is much lower than mechanical switches, right. Now, so using muxes and using a parallel combination, I am able to do two things, that I am able to make my digital wiring between the two temperature ranges as barely minimum as possible. So, let us go back to that slide and show you, just see here. Yes, this is just single line which carries signal between mux and readout. So, whenever there is a temperature interface, noise comes into picture, right, and that is where you need to keep your number of lines, active lines available to a bare minimum. That is the reason you use a mux in this case. Okay. And these are ideal for large quantum processors. They are being used in large quantum processors to a larger extent, right. What are the challenges? Very simple and easy challenges, like challenges which can be predicted a priori. One is of course the thermal constraint. Now, multiplexers needs to operate at very low power. Signal integrity, yes, of course, you need to preserve the signal fidelity, right, and then you need to have a cryo-CMOS stages attached to it. Obviously, the serial interfaces introduces delay as the port count increases, right. Why? Because as the number of port increases, you have to linearly increases your programming count in order to access all those ports in a serial fashion. Whereas, when you do a parallel interfacing, the programming cost reduces, the programming time reduces. Scalability, obviously the complexity increases with the number of qubits which you have written here, and you therefore need to minimize the control and the readout lines, right. The lower it is, the less complex the less complex is the overall design. Then there is another problem which will come into picture when you have very high integration happening at these scales, because there can be a problem of crosstalk between closely spaced signals. So, if say let us suppose you have two cryo-MUX signals going very close to each other, and these are digital signals, and one of the signal goes from 0 to 1, right, it is something like this. So, you have got two signals, cryo signals coming, and this goes from 0 to 1, and this was initially 0, you will see a spike coming here and going down, which is not a good sign. So, this is basically a victim and this is an aggressor, this is an aggressor and this is a victim. And integration, and therefore RF and digital interferences are an important issue as far as cryo-multiplexers are concerned. There is also difficulty in packaging MUX with other cryo-electronics, and this is primarily because of material and layout constraints, right. That is the major problem area which you face when you use a cryo. So, we have finished with MUX. MUX is given a basic idea about MUX. Let me give you the fundamental of a circulator. Circulators, so please understand this way that, okay, let me go ahead with this one and then I explain to you in terms of cryogenics, quantum computing. This is basically a 3-port device, right. It is a 3-port device which is port A, port B and port C. And what it does is it tries to route the signal in one direction. So, if a signal, especially in RF, right, if the signal is actually getting reflected back, we do not want the reflected signal to come back into the circulator. The circulator helps to move the signal or routes the signal in a unidirectional fashion, and that is what is written in this second point, that they route the signal in a unidirectional loop, you see. So, if it is moving in the clockwise fashion, it is basically always moving in the clockwise fashion. Now, why is it important? Because let us suppose the signal has generated from port A and wants to go to port B. Then when it is generated and goes to port B, there should not be any reflected signal from any. When I say reflected, I mean to say these are all microwave signals. If there is a reflection of the signal and it reaches any one of the quantum devices, some qubits, where it is not supposed to reach, it will destroy the state of the qubit, right. And therefore, they are essential in microwave systems, especially in quantum readout circuitry, and of course, they are useful in the cryogenic setups, right. So, they are the fundamentals of. So, what is the importance? They, as I discussed with you, they tend to isolate the qubit from back action of readout amplifier. So, when you do a readout amplifier, you amplify the signal, but then you also tend to, in a microwave domain, tend to reflect back. But if those reflections tends to change the state of the qubit, not a good idea. So, cryo-circulator sits in between the amplifier and the qubit such that the reverse signal do not change the state of the quantum states, and they are actually essential for quantum measurements and maintaining signal integrity. They are generally made of magnetically based ferrite material, and they exploit the concept of Faraday's rotation, right. They exploit Faraday's rotation. Please have a look at Faraday's rotation. They are available in standard RF books where you will get this concept here. And they operate efficiently at millikelvin temperature with minimal added noise, and they separate easily the incoming and outgoing microwave signals on the same line. So, in the same line, if you have an incoming and outgoing microwave signal, these circulators tends to bifurcate the two or do not let the two mix each other, right, and they can be used to therefore act as an isolator in a sense, right. Okay. These are some of the examples of the cryo-circulator, and this is what it looks like. This is what it looks like here. So, what it does here is, if you look if you look at this point, the first one is basically the spin qubit network, and this is basically a superconducting network. All of these are sitting at 20 to 100 Kelvin. Your circulators are sitting at about 4 Kelvin region, and they allow the flow of the signal only in the forward direction and not in the backward direction. So, there is no backward pull of signal going from the circulator, right, both for superconducting as well as for spin qubits in a sense, right. So, this is one example of circulator here. This is another example of circulator here in this case, right. This is an amplifier, single stage amplifier or multiple stage amplifier. This is a high electron mobility transistor which acts as a low noise amplifier. This is a local oscillator which adds the RF with the low frequency noise, and then it goes to a external filter for designing the overall readout circuitry. Now, what are the limitations? Like currently, the problem with circulators are they are very bulky in nature, which means that their areas are relatively very large, right, and therefore system level integration becomes much more difficult in the sense. Why? Because there is a heavy ferrite based devices. Now, two important points, their die area is very large and they have got high insertion loss, right. That is also a disadvantage of a cryo-circulator. Existing CMOS implementation are generally optimized for K band. K band is basically, typically they are only optimized for K band or GSM band, but not in the 5 to 8 gigahertz range where we require to operate the superconducting qubit. This is one of the practical problems of silicon based qubits, that you cannot operate at very high frequencies of 5 to 8 gigahertz, right, where actually the superconducting qubits actually work to a larger extent. So, that is one of the major challenges which you face for circulators. Typically, when you have these filter circulators there and you require, so if you are operating somewhere around 6 to 7 gigahertz, and then the problem is that the clock drivers which operate at 6.5 gigahertz, they will be actually dissipating large power from the clock drivers. So, there are clock which is being, so there are clock drivers available, right, and they drive the network. When they drive the network, they tend to dissipate very large amount of power. Cryo-circulator help them to do that to a larger extent, and that is one of the major limitation. And of course, as I told you, excessive power consumption is an unacceptable this thing, and then frequency multiplexing needs to be done. So, we do not want to do a time division multiplexing, but frequency division multiplexing across qubit will require a wide bandwidth. Now, wide bandwidth and low insertion loss is required. Both does not go well with the cryo circulators or the circulators, because they have got very high insertion loss and they do not operate at very high bandwidths, right. And that is one of the major limitations of cryo circulators in this case. And now, typically first CMOS circulator was designed, which operates at 4.2 Kelvin and uses an all pass filter architecture, and therefore it avoids all bulky transmission lines have been removed and all high frequency clock drivers. So, these are the two major bottlenecks of a circulator, that bulky transmission line and high frequency clock drivers, right. Typically the power they consume is 2.1 milliwatt, which is quite acceptable in terms of design, and they will support large bandwidth essential for frequency multiplexing qubit design, and operates at 5 to 8 gigahertz, which is the requirement for a spin qubit system, and they are very easily scalable. So, the current advances which is done is basically in silicon CMOS process, that they have low power, operate at 5 to 8 gigahertz, operate very easily at 4.2 kelvins, 4.2 Kelvin, they eliminate transmission line as well as high frequency clock drivers. I have already discussed with you the challenges for cryo-circulators. Obviously, the size and integration is the major challenge. Then similarly, magnetic field dependency is there for the cryo devices. Frequency compatibility is major issue, because you do not operate at 5 to 8, you operate at GSM. Power dissipation is very high, you have fabrication complexity because of the non-reciprocal device in standard CMOS processes. That is a basic major challenge. So, with this, let me recapitulate what we did in this lecture. We looked into, first of all, a multiplexer, right, and demultiplexer. So, multiplexer tends to have multiple input, one output. Demultiplexer has one single input and multiple output. So, this is what we learned, and we learned that this is sitting at around millikelvin region, so that the wiring and routing problems are barely minimum in this case. Then we looked into MUX challenges and its advances. Then we come to cryo-circulators, a circulator simply operating at lower temperature. They are primarily a 3-port device which routes signals only in one direction, and we saw that it helps you to reduce the bulk, the reflection from unwanted signals to the qubits. However, the cost you pay for it is very bulky, and therefore its integration is very difficult. Similarly, its power dissipation levels are relatively high, and you can't operate at 5 to 8 gigahertz where the quantum qubits will operate in a major fashion. So, with this we have been able to understand at least one section of the readout circuitry, which is basically the MUX and the cryo-circulators. I hope you enjoyed the lecture. Thank you very much.